Welcome back to Basic Biostatistics 2. This is session 5, Anova, or Analysis of Variance, that the abbreviation of Anova. In this session 5, you're going to see in 3 videos, among others, how to run a one-way Anova test and how to interpret the findings, how to get used to run a multi-way Anova test, how to test for possible interactions, and how to interpret the findings of the multi-Anova test correctly. I will also give you a short introduction into repeated measures ANOVA tests in SPSS, and in the end, we're going to run a couple of non-parametric tests for variables that are not normally distributed. ANOVA tests are used to compare mean values of a continuous variable among 3 or more groups. In the previous session, you have learned that a t-test compares the mean value of a continuous variable between 2 groups. However, if you have more than 2 groups, that happens quite often in research, we cannot use a t-test, but we have to use an ANOVA test instead. Let us use an example in our dataset. We would like to compare whether there's a statistically significant difference in the mean cholesterol values among the 3 physical activity categories, meaning that if the cholesterol level is different among the low, moderate, and high physical activity dwarfs. To do so, we need a one-way ANOVA test. ANOVA tests are found under Analyze, and under Analyze we go to Compare Means, the same place where I found t-tests, and here we scroll down to the last option we didn't use in the previous session, that is one-way ANOVA. We select one-way ANOVA and a new window pops up that is pretty simple and pretty easy to fill in. The dependent list is our continuous variable. For ANOVA, we have several assumptions. One assumption is that the continuous variable is normally distributed. The second assumption is that among the 3 groups, the standard deviation of the continuous variable is the same, or the variance is the same. I will come back to it once we see the output window to explain you what it actually means and how to test for it. So the dependent list is our continuous variable, that is cholesterol. We just click on cholesterol, we move it into the dependent list window, and now we have to decide what is the categorical variable, what are the 3 subgroups we like to have. As I mentioned, we like to see better physical activity in categories, have some different mean cholesterol levels. So we select physical activity categories and we move it to the factor window. So 2 very easy steps how to define the statistical test one-way ANOVA. However, before we continue, I would like to have post hoc tests. I will come back to it what it actually means. So by now I select post hoc tests, and we have here a lot of different post hoc tests. Post hoc test compares within the group's differences. For instance, in ANOVA, if we find out there are differences in the group, we don't necessarily know which group differs. There could be a difference in the mean cholesterol values between group 1 and 2, or group 1 and 3, or group 2 and 3. In order to know which group differ, we need post hoc tests, and probably a strong post hoc test for comparison between 3 groups is the LSD test. So I would select LSD in this example. You can Google the differences between the different post hoc tests. Some post hoc tests are better to compare mean values among more than 3 groups. Other tests are used to compare certain values with a reference value. For the time being, use LSD in all one-way ANOVA tests you do in this course. Once we click on continue, we are done with that part, and now please also would like you to go then to options, and under options I select usually descriptives that gives us the mean values for 3 groups and the standard deviations, and most important, the homogeneity variance test. This test tells us whether we can fulfill the second assumption of the ANOVA analysis and whether the variances are the same among the 3 groups. These 2 things are selected, descriptives, homogeneity variance. We click on continue, and then we click on OK. Once we click on OK, the tests are run. We end up with 4 different windows, 4 different tables, and I will go through the tables step by step. The first table, as you already know in SPSS, gives you descriptive statistics. So if you have three categories of physical activity, we have low, moderate, and high. The low category has 12 observations, moderate has 37 drafts, and the high category consists of 11 drafts. We have the mean cholesterol value of these three categories. We have the standard deviations, the standard error. We have the confidence interval for the mean, the minimal maximum, baseline, descriptive statistics of continuous variables. Now, the second assumption of Anova, the first one was that cholesterol levels normally distributed, and we know this already from session 2. The second assumption is there's no differences in the variances. The variance is the square root of standard deviation. So as a proxy, we can have a look at the standard deviation. So the assumption of the test is that the standard deviations are the same of the three groups. So there's no difference between 0.61, 0.43, 0.24 or better of their squared values. You will not know it looking at descriptive statistics. So basically we need to have a test. This test result is seen in the second table, test of homogeneity of variances. The null hypothesis is that there's no difference in the variances among the three groups of the mean value. The p-value here is bigger than 0.05, which means we accept the null hypothesis and we can state there's no differences in the variances and we fulfill the second assumption of the Anova test. This means we are doing well, we're doing great, we can continue with the test. If the homogeneity test of variance is not statistically significant, meaning that there are differences in the variance, we cannot use a one-way Anova test, but we have to use a non-parametric test. We'll come to the non-parametric test a bit later today. The third window, here we start basically with the whole Anova test results. Anova calculates here between group sum of squares, within group sum of squares. It actually divides then the between groups sum of squares by the degree of freedom and the within groups of squares to the degree of freedom. This gives you the mean squares, and then it divides you the mean square of between groups with the mean square of the within groups, and this is how the F value, the 47.357 value, comes from. So the test value of the Anova is the F value or Fisher value, which is 47.357. According to the F value, the program gives you a p-value. The null hypothesis was there's no difference in the mean values of cholesterol for three groups. Our p-value of the Anova test is statistically significant as it's below 0.05. This means that Anova showed that there's a statistically significant difference in the cholesterol values between the three groups. However, as you see, the test doesn't tell us which group differ from each other. If it's group 1 and group 3, or if there's a difference between group 2 and 3, or between group 1 and 3. In case the overall Anova or that test result is not significant, which means that there is no difference among the group, this is where you stop the analysis. Then you do not go to post hoc tests. You only go to post hoc tests if the overall Anova, that table we are talking about, is statistically significant. In case it's not significant, you just state no difference in the mean value among the three groups, full stop. In our case, however, the test is significant, less than 0.05, so we have differences. And this is why we go to the last table. And the last table are the post hoc test or the LSD test. It gives you pairwise comparisons between all subgroups. For instance, the first row compares low with moderate, so the mean value of cholesterol between the low and the moderate physical activity groups. We follow this up with the p-value. We see the p-value is smaller than 0.05. We conclude there's a significant difference in the cholesterol value between the low and the moderate physical activity groups. The second row compares low with high, so the category 1 and 3, where there's a difference in cholesterol value, mean cholesterol value between the low and the high physical activity group, and we see that this difference is also statistically significant. So by now we know there's a difference between the low and the moderate and the low and the high. The second row gives you what we are missing, the difference, where there's a difference between the moderate and the high physical activity groups. That difference is also statistically significant, and moderate with low or high with low and high moderate, the same actually we already have here. It's just the opposite. So we can state that actually all three means are different. So there's a difference in cholesterol level between the low and the moderate, between the low and the high, and the moderate and high physical activity groups. This is how to interpret the four tables of ANOVA. One more time, the problem with ANOVA is that even if you have a non-significant overall ANOVA result, it shows you the post hoc tests. But post hoc tests really are not valid or not important if the ANOVA is not statistically significant, because once we do not find a significant test result, we do not have to go to post hoc tests. What do we do if the continuous variable is not normally distributed, or the test of homogeneity variance is statistically significant, meaning that we have differences in the variance among three groups? In that case, unfortunately, we cannot use one-way ANOVA, but we have to use a non-parametric test. The corresponding non-parametric test to one-way ANOVA is the Kruskal-Wallis test. For instance, we go to Analyze, we go to non-parametric tests, and remember we add here the non-parametric test of the t-test as well. These are independent samples, as there are three different groups, different measurements. We select independent samples. We have here automatically compared distribution across groups. That's the correct one. As you can see, it gives us the Kruskal-Wallis test and one-way ANOVA test and Mann-Whitney tests. When we click on fields, here we decide what's our test variable, and we know that systolic blood pressure is not normally distributed, so we check that one, and we also compare it according to physical activity categories. So in this design, or our research question here is there a statistical significant difference in the mean systolic blood pressure for month 1 according to the three physical activity groups? As systolic blood pressure is not normally distributed, we cannot use an ANOVA test, but we use this non-parametric test called the Kruskal-Wallis test. We go then to settings. Usually ANOVA will, SPSS will identify automatically the correct test. If you do not want to do it, we go customize test and we choose the Kruskal-Wallis test. That is our test of choice for a non-parametric non-way ANOVA test. And this is actually all we have to do. And we click on run and we receive a very, very simple table that tells us actually the null hypothesis, meaning that the distribution of systolic blood pressure month 1 is the same across the categories. It tells you automatically the correct test, the Kruskal-Wallis test, and the p-value of the test. It also helps you telling you whether we have to reject the null hypothesis. So in this case, as the p-value is below 0.05, we reject the null hypothesis and we state that there are differences in systolic blood pressure across the three physical activity groups. However, we'll never know which group differ from each other in the Kruskal-Wallis test. This is how to run a Kruskal-Wallis test, and now by the end of this first video, you should know now how to program a one-way ANOVA test, what are the objectives of one-way ANOVA test. You should be able to interpret the four tables of the ANOVA test, and you should also be able to run a Kruskal-Wallis test for not normally distributed continuous variables. Thank you very much.